All right, I want to talk a little bit about equations here, and then I'm actually going to run an experiment. I'm going to do that as a separate recording just because I tried to do this just a moment ago, even though you aren't seeing that. And the first part was okay. The second part is where it kept messing up. So I want to start out with this equation right here. Now what this means is that the displacement an object has is equal to the initial velocity times the amount of time traveled plus 1/2 times the acceleration times time squared. Now what this equation does is it takes into account how fast an object's going, but also at the rate at which the velocity is changing. Now this equation is not one that you will see in Hewitt in this form. It is an equation that Hewitt does use, but he breaks it up into two different situations. So this is one of the constant acceleration kinematic equations, and that's important. It does assume that acceleration is constant. Now if I drop the vector symbols, then it becomes distance equals speed times time plus 1/2 times acceleration times squared, where acceleration is not how the rate at which velocity changes, but the rate at which speed changes. So if we look at a specific case, so if we say that the initial velocity is 0, so some object is starting at rest and then starts to fall, well, then the whole velocity term here drops out. This is no longer here. And so we're just left with that the displacement is equal to 1/2 times acceleration times squared. Now Hewitt doesn't use that equation quite yet. He takes it one more step. He says, let's assume that it's in free fall. So if we have initial velocity 0 and the object's in free fall, then that is the equation right there. Now he writes it slightly differently, but this in essence is an equation that Hewitt does use on page 43. So I have the vector symbols over it, and so we have displacement. Displacement is 1/2 times acceleration due to gravity, because it's free fall. This is the acceleration object has while it's falling, times time squared. Now over short distances, that acceleration is constant, and so this equation applies. If I'm talking about falling even 100 miles, it's still relatively constant. If I'm talking about falling 1,000,000 miles, well, probably not called falling at that point, but that equation starts to fall apart. But we're talking over short distances. We're doing fine on this. So page 43 in Hewitt, he has an equation very similar to this, and basically it's coming from a more general equation. Now the other piece of it is if we assume, again starting with this, if there is no acceleration. So that term drops out. And so if acceleration is 0, we're left with this. Now this is an equation, if you had even the basics of physics in middle school or physical science, whatever they called it, then you would have seen this one. This is one that most people understand intuitively, but you throw out a math equation and suddenly minds will blank. Not everyone, but some will. This is just basically, if I drop the vector symbols, distance equals rate times time. This is how far an object goes, or the displacement is equal to the velocity times time, or drop the vector symbols, distance equals speed times time. Now Hewitt does mention this on page 36 and 37, where he's using this equation right here. Now he takes it one step further. He says average speed or average velocity, and that actually is true. If acceleration is not constant, then it still works for average velocity. It's just a lot trickier to figure out. So this, again, distance equals rate times time is the most common expression of this, but more sophisticated, displacement equals velocity times time. I just wanted to bring up those two equations. We'll do a quick experiment using the first one right here. We'll see if we can actually figure out what is the acceleration due to gravity, and we'll go from there.